In the cold waters of the Norwegian Sea, nearly 1 kilometer below the surface, something is moving through a darkness so complete that sunlight has never reached it. It is deep red, it glows blue, and a single day of exposure to sunlight is enough to kill it. Its scientific name is Periphylla. Scientists often call it the Prince of Darkness. Both names are earned. This may be the most abundant deep-sea jellyfish on Earth, yet most scientists have never seen one alive. It broke one of the fundamental rules of jellyfish biology, abandoning a stage of life that almost every other jellyfish depends on to survive. When threatened, it releases a cloud of glowing blue slime into the water and disappears into the darkness. No other jellyfish is known to defend itself this way. It has 4 eyes in a world with no light. It glows in a place where almost nothing can see it glow. And despite looking impossibly fragile, it belongs to a lineage that has survived every mass extinction since long before the dinosaurs appeared. In the 1990s, swarms of Periphylla entered a Norwegian fjord and overwhelmed an ecosystem that had supported local fisheries for generations. There was nothing in the water capable of controlling them. Now, as parts of the ocean grow darker and warmer, the Prince of Darkness is expanding into places it has rarely been seen before. What makes Periphylla so strange is not any one feature. It is the way all of those features come together inside a creature that seems perfectly designed for a world most life cannot endure. Tonight, we're descending into the deep ocean to meet one of the oldest and most unusual animals still alive on Earth. If you enjoy this kind of content, a like and subscribe helps more people find it. And I'm curious, what brought you here tonight? Can't sleep, or just love this kind of thing? Let me know in the comments. Now, let's begin. A descent through the ocean is less like entering a body of water and more like passing through a series of invisible borders. The surface belongs to wind, waves, and sunlight. Far below, another realm begins. At around 200 meters, the last useful traces of daylight fade into the blue. Colors drain away, shadows lose meaning, the familiar world gives up its hold, and a different set of rules takes over. Oceanographers sometimes describe this transition as a journey from the twilight zone into the midnight zone. The names sound poetic, yet they are remarkably precise. In the twilight zone, a faint residue of sunlight still lingers overhead, too weak to illuminate the seafloor, but enough to hint at the existence of a sky. Deeper still lies the midnight zone, where light from the sun no longer reaches at all. There is no sunrise, no sunset, no horizon. Above and below become ideas rather than visible directions. This is the landscape Periphylla inhabits. Most individuals spend their lives well beneath 1,000 meters, where the weight of the ocean presses down with a force more than 100 times greater than that experienced at the surface. Temperatures remain cold and stable, commonly ranging between 4 degrees Celsius or 39 degrees Fahrenheit and 11 degrees Celsius or 52 degrees Fahrenheit. Nothing changes quickly here. Seasons arrive only as distant signals carried downward through layers of water. Some members of the species have been recorded at depths approaching 7,000 meters. At such depths, the pressure is so immense that the human body, built for life and air, would be unable to endure it. Yet for Periphylla, these crushing conditions are neither extreme nor unusual. They are simply home. Its range stretches across nearly the entire planet. From tropical oceans to polar seas, Periphylla drifts through waters separated by thousands of kilometers. Only the Black Sea stands outside its domain. Everywhere else, it appears as a recurring presence in the darkness, a traveler moving through one of Earth's largest habitats. In the waters surrounding Antarctica, the species reaches its greatest size. There, the ocean is colder, deeper, and darker than almost anywhere else. The immense southern waters seem to favor larger bodies, producing some of the biggest individuals ever documented. The conditions that appear hostile to most forms of life create opportunity for a creature shaped by scarcity. Scarcity governs everything in this world. Food may drift by only occasionally. Encounters with potential mates can be separated by vast distances and long stretches of time. Energy is precious. Every movement carries a cost. Every adaptation is measured against the relentless arithmetic of survival. For this reason, the deep ocean often rewards efficiency rather than strength. The animals that thrive here are not necessarily powerful. They are economical. They conserve, endure, and wait. Their lives unfold according to rhythms far slower than those near the surface. Periphylla moves between these layers with remarkable consistency. It spends part of its existence within the midnight zone, then ascends into the dim reaches of the twilight zone before returning once more to deeper water. The journey is repeated again and again across years and decades, following patterns established long before human beings ever looked beneath the waves. Seen from above, the ocean can appear like a single, uninterrupted expanse. Seen from within, it is a vast vertical landscape of distinct worlds stacked atop one another. Periphylla belongs to the deepest of those worlds, a place of pressure, cold, distance, and darkness. It is not merely surviving there. It was shaped there, refined there, and carried through immense spans of time by conditions that have changed very little since ancient oceans first closed over the planet. Among the countless drifting forms that inhabit the world's oceans, there exists a pattern so deeply woven into jellyfish biology that it appears almost universal. Long before a jellyfish develops its familiar bell and tentacles, long before it begins its life in open water, it usually passes through a very different existence. It begins as an egg, becomes a larva, settles onto a hard surface, and transforms into a tiny structure known as a polyp. Only later does the free-swimming jellyfish emerge. Across oceans and across evolutionary time, this sequence repeats itself again and again, linking species that otherwise look remarkably different from one another. The polyp is more than a stage in development. It is a foundation. Anchored to rock, shell, or seafloor, it acts as a living reserve from which future generations can emerge. In many jellyfish species, the polyp reproduces without a mate, producing new individuals through repeated budding. It endures changing conditions, survives periods of scarcity, and serves as a biological foothold that allows populations to recover even after severe losses. The arrangement is so effective that it became one of the defining characteristics of the group itself. Yet Periphylla drifts through the ocean, having abandoned this pattern entirely. At some point in its distant evolutionary history, the species stepped away from a strategy that had served jellyfish lineages for hundreds of millions of years. The familiar anchor disappeared, the attachment to the seafloor vanished, the reset mechanism shared by so many relatives was left behind. From the moment life begins until the moment it ends, Periphylla remains suspended within the water column, carried through the deep by currents, migrations, and its own movements. Biologists describe this condition as a fully pelagic existence. Every stage unfolds in open water. There is no period spent attached to the bottom, no hidden colony waiting in reserve, no nursery fixed to stone in some protected corner of the sea. The entire life cycle plays out within an environment defined by movement. Among the true jellyfish, this arrangement is exceptionally uncommon. The broader branch of life to which Periphylla belongs contains species whose histories are tied intimately to the seafloor. Periphylla stands apart from that tradition. Its development follows a route that appears less secure at nearly every step. Each new individual must begin as an egg released into the vastness of the ocean. Each developing juvenile must survive exposure to currents, predators, and changing conditions without the protection offered by an attached stage. There is no opportunity to multiply through budding colonies, no hidden population waiting below to replenish losses. Every generation depends upon the success of individual offspring making their way through a world that offers very little shelter. On paper, such a strategy appears fragile. Evolution often favors redundancy, backups, and alternative pathways. Periphylla seems to possess none of them. It places nearly everything on a single route, trusting each generation to navigate the abyss alone, and yet the outcome is the opposite of what that vulnerability suggests. Rather than becoming rare, Periphylla spread through nearly every major ocean basin. Rather than remaining confined to isolated pockets, it established itself across enormous geographic ranges. Rather than fading beneath the pressures of deep ocean life, it became one of the most successful gelatinous predators in the environments it occupies. The contradiction sits at the center of its story. An animal that discarded one of the most dependable tools available to jellyfish should have narrowed its chances of survival. Instead, it expanded them. A life cycle that appears precarious has persisted across immense spans of time. A reproductive strategy that seems to invite failure has produced a species capable of thriving in some of the most demanding habitats on Earth. Periphylla did not merely bend a biological rule, it carried on as though the rule had never existed at all. If Periphylla were placed beside many of its jellyfish relatives, the difference would be apparent long before it began to move. There is a sense of deliberate structure to its form, as though every contour has been refined for a particular existence. Nothing about its body appears ornamental. Each feature seems shaped by long residence in a realm where wasted energy carries a cost. The bell rises upward in a steep, tapering profile, reaching heights of around 35 centimeters and widths of approximately 30 centimeters. Rather than resembling the broad umbrella shape familiar from many coastal jellyfish, it forms something closer to a crown or a pointed ceremonial cap. Around the lower portion runs a distinct circular indentation known as the coronal groove, a feature so characteristic that it helped define the entire group to which Periphylla belongs. Viewed from certain angles, the groove gives the animal a layered appearance, as though its body were divided into separate architectural tiers. Despite this substantial size, the creature remains astonishingly light. A typical individual weighs about 540 grams. Between 90 and 96% of that mass consists of water. The remainder is a delicate framework of proteins, tissues, and gelatinous structures arranged with remarkable efficiency. There is very little excess. Almost every component serves more than one purpose. Extending from the lower rim of the bell are 12 tentacles. They are unlike the long trailing filaments associated with many familiar jellyfish. These structures possess a firmer appearance and a greater degree of control. They can respond rapidly when prey comes within reach, transforming the animal from a drifting silhouette into an active hunter. The capture sequence unfolds with unusual precision. Once prey is intercepted, the tentacles begin folding inward in a spiraling motion. The movement resembles the turning of a corkscrew, each contraction drawing the captured animal closer to the center of the body. Marine biologists refer to this behavior as the corkscrew reaction. Among jellyfish, it stands as a distinctive solution to the challenge of feeding in open water. Instead of relying solely on chance contact, Periphylla actively guides its catch toward the mouth through coordinated movements of the tentacles themselves. The coronal groove contributes to this process. As prey is maneuvered inward, the groove helps contain and direct it, reducing the likelihood of escape during the final stages of capture. What appears at first to be a simple anatomical feature becomes part of an integrated feeding system, one component working alongside another in a design refined through immense spans of evolutionary time. Its coloration is perhaps the most striking feature of all. Periphylla possesses a deep red body, often so dark that it appears almost black in dim conditions. This color comes from a pigment known as protoporphyrin. The pigment serves a purpose far more important than appearance. Many of the animals consumed by Periphylla produce their own light. After being swallowed, they may continue glowing within the predator's body. In the darkness of the deep ocean, such internal illumination could reveal the jellyfish's location to anything nearby. Protoporphyrin solves this problem. The pigment absorbs the bioluminescent glow of ingested prey, preventing that light from shining through the translucent tissues. The meal remains hidden behind a red shield. The hunter carries its food invisibly through the darkness, leaving no luminous trail behind. Around the rim of the bell sit 4 sensory structures known as rhopalia. These organs contain primitive light-detecting systems capable of registering changes in illumination. Though far simpler than the eyes of fish or mammals, they provide awareness of brightness and orientation. Their presence gives Periphylla an unusual appearance, a creature equipped to sense light while spending much of its existence beyond the reach of the sun. Perhaps most remarkable is how little this design appears to have changed. Across hundreds of millions of years, through shifting continents, changing oceans, and entire chapters of Earth's biological history, the essential architecture endured. The body drifting through modern seas remains recognizably linked to forms that inhabited ancient waters when the earliest fish were only beginning to develop the skeletal foundations that would later transform life across the planet. Long before human beings learned to create lamps, fires, or cities bright enough to be seen from space, living organisms had already mastered the production of light. Across the oceans, countless species evolved the ability to generate brief flashes, glowing trails, pulses, and signals. Among jellyfish, however, this ability remains surprisingly uncommon. Out of roughly 200 known species belonging to the true jellyfish group, only about 5 possess confirmed bioluminescence. Periphylla belongs to that remarkably small company. Its glow accompanies it through every stage of life, from the earliest moments after hatching to the final days of an individual that may have drifted through the ocean for decades. The capacity remains present. It is woven into the animal's biology so completely that there is no phase in which it disappears. The light does not arrive later in development, it begins at the beginning. The color itself is not the pale white often associated with luminescence. Instead, it emerges as a vivid blue-green radiance, one of the most effective wavelengths for traveling through seawater. When stimulated by touch, disturbance, or other triggers, luminous waves spread across the body. The effect resembles a moving current passing through living tissue. Light races outward from the point of activation, traveling across the bell at speeds approaching 60 centimeters per second. What begins as a single spark becomes a flowing pulse, expanding through the animal in visible patterns. For researchers fortunate enough to witness the phenomenon, the display appears surprisingly organized. The light does not erupt randomly, it propagates in coordinated sequences, suggesting a biological system refined through immense stretches of evolutionary time. The glow behaves almost like a message moving through a network, each region responding in turn as the luminous signal advances. The exact purpose of these displays remains a subject of continuing study. Some scientists believe the light functions as a warning. Many predators learn to associate vivid signals with unpleasant experiences, and Periphylla's tissues are thought to be unpalatable to a wide range of animals. A sudden burst of blue-green light may therefore serve as an advertisement of toxicity, discouraging attacks before they fully develop. Other researchers suggest the glow can create confusion during encounters with predators. In an environment where vision is often limited and brief flashes carry disproportionate importance, an unexpected pulse of light may disrupt an attack long enough for the jellyfish to escape. There is also growing interest in the possibility that the displays carry information between members of the species themselves, transforming illumination into a form of communication carried through the water. Yet all of these possibilities lead toward a contradiction embedded deep within the body of Periphylla. The same pigment responsible for its deep red coloration, the compound known as protoporphyrin, performs valuable functions throughout its life. It conceals the lingering glow of consumed prey and contributes to the animal's distinctive appearance. But hidden within that advantage lies a remarkable vulnerability. When exposed to ultraviolet radiation from sunlight, protoporphyrin undergoes a destructive transformation. The pigment becomes chemically reactive, initiating a cascade of damage within surrounding tissues. Instead of protecting the animal, it begins harming it. In Periphylla, the effects extend into the nervous system itself. Signals become disrupted, movement deteriorates. The coordinated rhythms that govern the body begin to fail. The process is not merely stressful or debilitating, it is lethal. A prolonged encounter with daylight does not leave Periphylla weakened and recovering. It dismantles the mechanisms that allow the animal to function. The body gradually loses its ability to coordinate movement, and survival becomes impossible. The very chemistry that provides advantages in darkness becomes dangerous under the sun, and so Periphylla carries within itself an extraordinary duality. Throughout its life, it generates living light, sending blue-green pulses across its body in displays refined across ancient ages. Yet embedded beside that brilliance is a molecular weakness so profound that direct sunlight can bring the entire system undone. The glow and the danger are inseparable, bound together within the same creature, each existing because of the other. The day of a Periphylla does not begin with sunrise. It begins with withdrawal. As brightness gradually returns to the upper layers of the sea, the jellyfish turns downward and sinks into greater depths, moving away from a danger woven into its own biology. Hours later, when darkness once again spreads across the water above, the direction reverses. The ascent begins. This pattern repeats with remarkable consistency. Across the fjords of Norway, researchers monitoring populations over long periods discovered that the overwhelming majority of individuals participate in the same daily journey. Between roughly 80 and 90% of the population travels vertically through the water column every day of the year, not during a particular season, not only during periods of reproduction. The movement persists through changing weather, shifting currents, and passing years. It becomes the framework around which an entire life is organized. The distances involved are substantial. Many individuals move between 200 and 400 meters during a single migration cycle. For an animal whose body is composed primarily of water and gelatinous tissue, the effort is considerable, yet the movement unfolds patiently, powered by repeated contractions of the bell. Periphylla is not a fast swimmer. At maximum speed, it reaches only a little more than 10 centimeters per second. Compared with fish, squid, or marine mammals, the pace appears almost leisurely. Covering hundreds of meters, therefore, requires time. The ascent may take hours, a gradual climb through layers of water that differ in temperature, density, and available food. The destination is not random. Higher in the water column, conditions become more favorable for feeding. Small drifting animals gather in greater concentrations, creating opportunities unavailable farther below. By rising into these regions after darkness has settled, Periphylla gains access to resources while avoiding the threat posed by daylight. Feeding and protection become linked to the same rhythm. Then the cycle reverses once more. Long before the return of direct sunlight, Periphylla begins descending. The retreat starts while the upper ocean remains dark to human eyes. The timing reflects a life shaped by extraordinary sensitivity to illumination. Rather than waiting for danger to arrive, the jellyfish leaves in advance, abandoning the shallower layers before the first traces of morning can penetrate downward. This daily migration is not unique to Periphylla. Throughout the world's oceans, immense numbers of animals perform similar movements. Tiny crustaceans, fish, squid, and gelatinous organisms rise after dusk and descend before dawn. Together they create one of the largest biological movements on Earth. Measured by total biomass, the collective migration involves countless millions of organisms moving in synchrony across the planet every single day. Periphylla participates in this vast procession, yet it does so according to its own limitations and opportunities. Larger adults frequently travel closer to the surface than younger individuals. Researchers suspect mature jellyfish possess a slightly greater tolerance for low levels of illumination, allowing them to exploit feeding grounds unavailable to smaller members of the species. Juveniles tend to remain deeper, maintaining a larger margin of safety. The ascent appears to serve another purpose as well. During these nightly journeys, adults enter the same layers of water and become more likely to encounter one another. Scientists believe this is when reproduction most often occurs, in a habitat where individuals may otherwise be separated by great distances. The migration acts as a gathering point, bringing potential mates into closer proximity within the darkness. Over years and decades, the pattern becomes almost metronomic. Upward through the water after nightfall, downward before dawn, feeding above, refuge below. The movement repeats so faithfully that it resembles a biological heartbeat stretched across an entire lifetime. Every stage of existence is arranged around changing levels of light, and every journey follows the same enduring principle. Periphylla does not merely inhabit darkness. It moves through the ocean in step with darkness itself, tracing its boundaries day after day through the vast vertical landscape of the sea. In much of the natural world, survival depends on constant acquisition. Birds search for food from dawn until dusk. Predators pursue prey across plains, forests, and oceans. Energy is spent in order to gain more energy. Periphylla follows a different philosophy, one shaped by a habitat where abundance is uncommon and opportunities arrive slowly. Rather than building its existence around pursuit, it has evolved around conservation. Measurements of its oxygen consumption reveal just how far this strategy extends. Researchers studying the species discovered metabolic rates among the lowest ever recorded for a predatory animal of comparable size. The amount of oxygen required to sustain its body ranges from roughly 0.4 to 5 6 microliters per milligram of carbon each hour. Beneath the technical language lies a simple reality. Periphylla operates on an extraordinarily small energy budget. The consequences of that economy are remarkable. An individual can persist on surprisingly little food, sometimes requiring only a handful of prey organisms across an entire day. Depending on conditions and body size, survival may be sustained by as few as one prey item or several dozen. For a predator inhabiting one of the most resource-limited environments on Earth, such restraint becomes an enormous advantage. Its menu consists largely of small drifting animals carried through the water column. Copepods form an important part of the diet. These tiny crustaceans are often smaller than a grain of rice and occur throughout the world's oceans in immense numbers. Alongside them come pteropods, amphipods, krill, arrowworms, small fish, and occasionally other jellyfish. None represent particularly large meals. Instead, Periphylla survives through a steady accumulation of modest opportunities. What makes this possible is not speed or aggression, but efficiency. The animal spends long periods suspended in the water, allowing currents and migrations to bring potential prey within reach. Every movement is measured against its cost. Every contraction of the bell must justify the energy required to perform it. In a realm where meals may be separated by long intervals, waste becomes a greater threat than hunger itself. This economy extends into some of the most unusual behaviors ever documented in a jellyfish. When disturbed by turbulence or sudden contact, Periphylla may withdraw its tentacles inward, concealing them within its own body. Under certain circumstances, it can also shed tissue from the tips of those tentacles. The detached fragments are loaded with stinging cells and remain active after separation. The result is extraordinary. Pieces of the animal continue functioning as traps even after they have broken away. Tiny organisms drifting through the water become entangled in the discarded tissue, where the stinging structures remain capable of capturing prey. What begins as a response to disturbance transforms into an additional method of feeding. Researchers eventually uncovered this behavior through an unexpected discrepancy. Specimens observed alive with remotely operated vehicles often appeared to contain very little food. Their stomachs might hold only 1, 2, 3, or 4 prey items, yet individuals collected by traditional nets frequently contained much larger quantities. At first, the difference seemed puzzling. The explanation emerged from the collection process itself. Animals caught in nets experience stress and physical disturbance. In response, many shed tentacle tissue before retrieval. That detached material continued trapping prey, which then accumulated around the specimen. The fuller stomachs and tangled captures were not evidence of a more active hunter. They were evidence of a creature responding to disruption in a way that simultaneously increased feeding opportunities. Few predators could afford such patience. Periphylla can. Its body consumes little. Its movements are restrained. Its methods rely as much on waiting as on action. Over years that stretch into decades, it drifts through the ocean carrying an energy strategy almost perfectly suited to scarcity. While other animals survive by finding more food, Periphylla survives by needing less of it, turning endurance itself into one of the most effective hunting tools in the deep sea. The observation began with an accident. A diver working in the cold waters of a Norwegian fjord came into unexpected contact with a drifting Periphylla. Encounters of this kind are uncommon. The species spends much of its existence beyond the reach of ordinary human activity, inhabiting depths where direct observation is difficult. Yet, on this occasion, a brief touch triggered one of the most unusual defensive displays ever recorded in a jellyfish. For an instant, the animal transformed. Its deep crimson body flashed pale, shifting from dark red to brilliant white with startling speed. The change lasted only a moment before the original coloration returned. Then came a second response, stranger still. From the margins of its body, Periphylla released a luminous cloud into the surrounding water, a scattering of glowing blue particles that expanded outward like a drifting constellation, suspended in liquid darkness. Unlike the waves of bioluminescence that travel across the bell, this was not light confined within living tissue. It was matter itself. Tiny luminous particles were physically expelled into the water and left behind as the jellyfish moved away. The glowing material lingered independently, continuing to shine after separation from the animal that produced it. At the same time, Periphylla reacted with unusual urgency. Powerful contractions rippled through the bell. The body pivoted, accelerated, and departed from the immediate area, leaving the suspended cloud behind. For a creature that normally survives through patience and energy conservation, the response represented a significant investment of effort. The distinction between this behavior and ordinary bioluminescence is important. Many marine organisms produce flashes or pulses from their own bodies. Periphylla itself regularly generates moving patterns of blue-green light across its tissues. In those cases, the source and the signal remain connected. Here, the light becomes detached. The luminous particles form a separate object within the water, existing for a time as an independent beacon. Researchers refer to this phenomenon as secretory bioluminescence. Rather than illuminating itself, the jellyfish releases illumination into the environment. The strategy is remarkably uncommon, and among jellyfish, it appears in a form unlike anything documented elsewhere. The purpose becomes easier to understand when viewed from the perspective of a predator. Imagine an attack beginning in darkness. Contact is made. Suddenly, a brilliant cloud erupts nearby, filling the water with moving points of light. Attention shifts toward the glowing disturbance. In that brief interval, the intended target is already swimming away. Marine biologists often compare the effect to a burglar alarm. The light does not necessarily stop an attacker directly. Instead, it creates a conspicuous event that may attract the attention of larger predators in the vicinity. The original hunter becomes vulnerable to becoming hunted. Whether through distraction, confusion, or redirected risk, the glowing cloud changes the situation in Periphylla's favor. Observations in controlled environments have confirmed that the behavior is genuine and repeatable. Encounters in natural settings have demonstrated that it is not merely an artifact of laboratory conditions. Yet despite these confirmations, many details remain uncertain. The precise chemical composition of the secreted particles has not been completely resolved. Scientists continue investigating exactly what conditions trigger release, how sensitive the response may be, and how often an individual can perform the behavior before exhausting its supply of luminous material. The rarity of direct observations contributes to the mystery. Periphylla inhabits regions where prolonged study remains challenging, and many interactions occur far beyond the reach of human observers. Each recorded event therefore offers only a brief glimpse into a behavior that may have been refined over immense stretches of evolutionary history. What emerges from these observations is a portrait of a defense perfectly suited to the constraints of its environment. Periphylla is not built for speed. It cannot vanish into coral reefs or disappear among dense vegetation. The open water offers few physical refuges. Instead, it manipulates attention itself. A burst of light appears where the predator expects prey to be, while the actual animal moves elsewhere. In doing so, Periphylla achieves something remarkable. It uses illumination as concealment. The glow reveals one thing in order to hide another, turning brightness into a form of camouflage and making darkness and light work together in the same act of survival. Along the rim of Periphylla's bell sit four small structures that, at first glance, seem almost out of place. They do not resemble eyes in any familiar sense. There are no pupils, no lenses capable of forming images, no intricate visual machinery comparable to that found in fish, squid, or mammals. Yet, these organs have persisted through immense stretches of evolutionary time, retained generation after generation, as though they continue to provide information of profound importance. These structures are known as rhopalia. Each one combines multiple sensory functions within a compact package. They contain receptors sensitive to gravity, allowing the jellyfish to maintain orientation in the water, and cells capable of detecting changes in light intensity. Together, they provide a basic awareness of direction and illumination, helping coordinate movement through an environment where conventional landmarks do not exist. For many jellyfish, such abilities are easy to understand. Species inhabiting coastal waters encounter changing sunlight throughout the day. They rise and descend through illuminated layers, responding to brightness as they navigate. Light detection serves an obvious purpose. Periphylla presents a more complicated case. Much of its life unfolds in regions where sunlight never arrives. Vast periods pass beneath layers of water so thick that day and night become nearly indistinguishable. In such places, a sensory system devoted solely to monitoring brightness would seem increasingly irrelevant. Evolution tends to reduce structures that no longer provide meaningful advantages. Yet, the rhopalia remain. That persistence has encouraged scientists to consider another possibility. Periphylla is not entirely surrounded by darkness. It inhabits a world filled with living light. Countless deep-sea organisms produce flashes, pulses, and glows of their own. Among them is Periphylla itself. Every individual carries the capacity to generate luminous displays that travel across its body in organized waves. If the rhopalia are capable of detecting faint sources of light, then those displays may be visible not only to predators and prey, but also to other members of the species. From this idea emerges one of the most intriguing hypotheses in deep ocean biology. Researchers have proposed that Periphylla may use bioluminescence as a form of communication. The concept remains under investigation, and direct evidence is still incomplete, yet the possibility is difficult to ignore. In a habitat where individuals may drift great distances apart, visual signals possess certain advantages. Light travels efficiently through seawater. It can announce presence, reveal location, and transmit information without requiring physical contact. A brief pulse might indicate readiness to reproduce. Another pattern could serve as a warning. Repeated flashes may help individuals maintain awareness of one another during migrations through the water column. The exact meanings, if meanings exist at all, remain unknown. What matters is that the biological machinery for both sending and receiving signals appears to be present. This interpretation casts familiar observations in a different light. The luminous waves moving across the bell are often described as defensive displays, and they may indeed serve that role. Yet defense and communication are not mutually exclusive. The same signal can carry different information depending on who receives it. What appears to one observer as a warning may appear to another as a message. The idea becomes even more striking when considered alongside the peculiar vulnerabilities already woven into Periphylla's biology. Here is a creature whose relationship with light is defined by contradiction. It depends on darkness for survival. It possesses sensory organs capable of detecting illumination. It produces its own luminous displays. And the same broader force, represented by light, eventually becomes lethal under the wrong conditions. Within the deep ocean, many familiar assumptions seem to reverse themselves. Scarcity creates abundance for some species. Slowness becomes an advantage. Fragility coexists with endurance. Periphylla fits naturally into that pattern of inversion. If these glowing signals truly function as communication, then conversations may be unfolding continually through waters where sunlight never reaches. For now, the content of those exchanges remains hidden. The Rhopalia detect, the bell responds, waves of light travel across living tissue and disappear into the surrounding darkness. Science can observe the signals, measure their speed, and document their occurrence. The meaning behind them, if meaning exists, continues to drift just beyond translation, carried through the deep by a language no human being has yet learned to read. Most marine animals place their offspring somewhere. Fish scatter eggs among vegetation or release them into currents timed to carry them toward favorable conditions. Many jellyfish rely on anchored stages attached to hard surfaces. Even creatures living in immense oceans often seek some form of stability at the beginning of life. Periphylla does something far more uncertain. It lets go. When reproduction occurs, the eggs are released directly into open water. There is no protective chamber, no attachment point, no carefully chosen nursery hidden among rocks or seafloor structures. The developing young enter a world of movement immediately, suspended within the water column and carried by forces far larger than themselves. Their position is determined not by parental guidance, but by the physical properties of the sea. Temperature, salinity, and density interact to create layers throughout the water column, and the eggs settle into these invisible boundaries. The result is a form of incubation governed less by biology than by physics. The ocean itself becomes the vessel in which development unfolds. For months, the eggs remain adrift. During this period, they are passengers in a landscape defined by currents, gradients, and circulation patterns. Unlike mature individuals, they cannot undertake migrations through the water. They cannot retreat from danger. They cannot seek food or alter their depth through deliberate movement. Their fate depends almost entirely upon remaining within the correct portion of the environment long enough for development to continue. The process from fertilization to an actively feeding juvenile generally requires between 2 and 3 months. During that time, the future jellyfish exists in a state of extraordinary vulnerability. Every current matters. Every shift in water structure matters. A mature periphylla possesses adaptations accumulated across years of growth. An egg possesses only patience. This dependence becomes particularly important within fjord ecosystems. Beneath the surface, fjords contain complex layers of water separated by depth and density. Near their entrances often lies a submerged threshold, a geological barrier that influences how water moves into and out of the basin. For developing periphylla, remaining below this threshold can be essential. Eggs and very young juveniles are especially sensitive to large-scale renewal events that periodically replace deeper fjord waters. During such episodes, incoming water masses can alter circulation throughout the basin. Individuals too young to control their position may be carried away from the conditions required for survival. Entire groups of developing offspring can disappear from a fjord in a single event, not because they were eaten or outcompeted, but because the physical structure of the water changed around them. Against such losses, periphylla relies on a strategy rooted in time rather than speed. Young females produce relatively few mature eggs. At around 3 years of age, a female may carry approximately 10. This number appears modest when compared with many marine organisms that release vast quantities of offspring early in life. Yet periphylla is not built around early abundance. Its reproductive investment grows steadily with age. As the years pass, the number of eggs increases dramatically. By around 9 years of age, a female may carry more than 1,000 mature eggs. The transformation is striking. Reproduction becomes progressively more productive as the animal survives longer, creating a powerful connection between longevity and population growth. For many species, reaching adulthood is the primary objective. In Periphylla, survival beyond adulthood continues generating advantages year after year. Each additional season preserved means greater reproductive capacity. Each year accumulated in the deep becomes a contribution to future generations. The pattern reflects the broader rhythm of the species itself. Nothing happens quickly. Development takes time. Growth takes time. Reproduction expands gradually across a long life. The eggs drift through the ocean without protection, exposed to forces capable of removing them at any moment. Yet the species persists because it has built its strategy around endurance. A female that survives for decades becomes more than an individual organism. She becomes a reservoir of future offspring, carrying within her the accumulated reproductive potential of years spent successfully navigating one of the most demanding environments on Earth. The beginning of a Periphylla's life is defined not by survival, but by loss. Long before an individual grows large enough to migrate through the water column or participate in the ancient rhythms of adulthood, it enters a period in which death is overwhelmingly more likely than life. The odds are so extreme that they almost seem incompatible with the success of the species itself. Among the eggs released into the deep ocean, somewhere between 93% and 99 and 95/100% will never reach a diameter of 1 centimeter. The overwhelming majority vanish before their journey has truly begun. In some reproductive cycles, fewer than 1 out of every 2,000 eggs survives long enough to become a juvenile capable of continuing development. Such mortality might suggest relentless predation, yet predators are not the principal cause. The greatest threat comes from the water itself. Within fjords, the deep layers do not remain unchanged forever. Periodically, new masses of colder, oxygen-rich water move into the basin and displace older water already present at depth. These renewal events are part of the natural circulation of the system, helping maintain the chemical balance of the fjord. For many organisms, they are beneficial. For the youngest Periphylla, they can be catastrophic. Eggs and newly developing juveniles possess little control over their position. Suspended within specific layers of water, they depend on stability. When renewal events occur, entire groups may be transported away from the conditions required for development. Some are carried beyond the depths where they can survive. Others are swept into environments unsuitable for continued growth. The result is not the gradual loss of individuals, but the sudden disappearance of entire cohorts. A generation can be reduced dramatically by forces that never touch a single predator's mouth. Yet despite this relentless attrition, Periphylla populations persist. In certain fjords, they do more than persist. They become dominant. The explanation lies in a strategy that values duration over immediacy. A mature Periphylla may survive for decades. Across those years, reproduction continues. Egg production increases. Opportunities accumulate. Each individual becomes a long-term contributor to future generations, steadily replacing losses through persistence rather than abundance at any single moment. Growth itself reflects this philosophy. During the first year of life, a juvenile expands at a relatively rapid pace, increasing in size by roughly 55/100% of its body dimensions each day. At this stage, development remains the priority. Energy is directed toward building the structures needed for survival in the demanding conditions of the deep ocean. As the animal ages, the pace gradually slows. By approximately the fourth year, daily growth rates fall below 0.17%. The change is not a sign of failure. It represents a shift in investment. Resources once devoted primarily to increasing body size begin flowing toward reproduction. Around the third year, the first mature eggs begin to appear in females. By the ninth year, reproductive capacity has expanded dramatically, with some individuals carrying well over 1,000 eggs. What emerges is a life history built upon accumulation. The longer an individual survives, the more valuable that survival becomes. This creates a remarkable balance. Vast numbers of offspring disappear before reaching even the earliest milestones of development. At the same time, the adults that endure continue producing new generations year after year. The losses are enormous, yet the reproductive engine never truly stops. Viewed across a single season, the numbers appear almost impossible. Viewed across decades, they begin to make sense. Periphylla does not depend on rapid success, it depends on continuity. The species accepts extraordinary mortality at the beginning of life because it compensates through extraordinary persistence afterward. In many environments, speed is rewarded. Fast growth, rapid reproduction, and short generational cycles create advantage. The deep ocean follows different rules. Time stretches, processes slow. Survival itself becomes a resource. Within that world, Periphylla succeeds not because its young are protected, but because enough adults remain alive long enough to keep trying, generation after generation, allowing endurance to accomplish what abundance alone never could. Life in the deep ocean is often described as a chain of consumption. One creature survives by finding another. Every drifting body, every swimming shadow, every fragment descending from above eventually becomes nourishment for something else. Energy is scarce, and scarcity encourages opportunism. In such a place, few animals remain uneaten for long. Periphylla exists as one of the rare exceptions. Across the vast darkness where it spends most of its life, the list of animals willing to consume it is surprisingly short. This is not because Periphylla is difficult to find. Mature individuals can become abundant in certain regions, gathering in numbers large enough to dominate entire water columns. Nor is it because the jellyfish possesses exceptional speed. Its movements remain measured, conserving energy rather than expending it. The explanation lies within the animal itself. The deep red coloration that has accompanied Periphylla through millions of years is more than an outward characteristic. Embedded within its tissues is the pigment protoporphyrin, the same substance that shapes many of the creature's unusual biological traits. Earlier, this pigment revealed its role in absorbing the glow of swallowed prey and in creating a dangerous vulnerability to sunlight. It appears to serve another purpose as well. Evidence suggests that it makes the jellyfish profoundly unappealing to potential predators. Animals encountering Periphylla may discover that it is not worth eating. The tissues are believed to be toxic or chemically unpleasant, creating a powerful deterrent against repeated attacks. In an environment where energy cannot be wasted, predators quickly learn which meals provide reward and which bring only difficulty. Its displays of bioluminescence may reinforce that lesson. Rather than functioning solely as a defensive distraction or possible form of communication, the luminous pulses may also serve as a warning. Across the darkness, the flashes announce the presence of an animal that carries its own chemical protection. Light becomes a message attached to taste, memory, and survival. As a result, remarkably few species have been documented feeding upon Periphylla. Below depths of roughly 1,000 meters, two fish have been observed consuming it. One is the deep-sea species Alepocephalus bairdii. The other is Coryphaenoides rupestris. Both inhabit the cold depths where encounters with Periphylla are possible, yet neither exists in numbers capable of exerting significant pressure on jellyfish populations. Their presence represents predation, but not population control. A third predator emerges from a different branch of ocean life. The deep-sea shrimp Notostomus robustus has also been identified as a consumer of Periphylla. Even here, however, the relationship appears limited rather than transformative. Beyond these examples, the roster grows only slightly. Certain sea spiders have been recorded feeding upon the jellyfish. In Antarctic waters, some anemones have joined the list as well. After that, the catalog of known predators becomes remarkably sparse. For an animal spread across oceans and capable of reaching extraordinary abundance, the absence of enemies is striking. Many deep-sea species survive by avoiding detection. Others depend upon camouflage, speed, armor, or numbers. Periphylla benefits from something rarer. It occupies a habitat where few predators exist, possesses chemistry that discourages attack, and reinforces that chemistry with visible warnings whenever necessary. The result is an unusual position within the ecology of the deep. Periphylla remains a predator itself, consuming the small drifting animals that sustain its long life. At the same time, almost nothing hunts it in sufficient quantities to influence its success. In many fjord systems, there is effectively no natural force removing individuals quickly enough to limit population growth. Through the convergence of toxicity, depth, and bioluminescent signaling, Periphylla has achieved a status uncommon among gelatinous animals. It drifts through one of the most demanding environments on Earth while carrying remarkably little fear of becoming food. In a realm where nearly everything exists within another creature's menu, Periphylla has moved close to the end of the chain, occupying a place with very little above it and an immense darkness stretching below. 4 decades ago, the waters of Trondheim's fjord supported one of Norway's most productive fisheries. Generations had worked these waters, drawing cod, haddock, herring, and sprat from a system that seemed stable enough to endure indefinitely. The fjord functioned as a living network of relationships built over centuries, each species occupying a place shaped by food, habitat, and season. To those who depended upon it, the balance appeared permanent. Yet, ecosystems rarely announce the beginning of change. At first, Periphylla was simply present. Individuals appeared in the fjord in numbers greater than expected, drifting through depths that had long supported thriving fish populations. Their arrival did not resemble an invasion in the way humans often imagine one. There was no dramatic moment, no visible boundary crossed. The transformation unfolded gradually, hidden beneath the surface, among eggs, larvae, and the countless small organisms that sustain marine food webs. As the years passed, the jellyfish became increasingly abundant. By the time scientists began to understand the scale of what was occurring, the effects were already spreading through the ecosystem. The challenge posed by Periphylla was not limited to competition. Many marine species compete for similar resources without causing collapse. Periphylla exerted pressure at multiple levels simultaneously. It consumed tiny crustaceans that juvenile fish depended upon for growth. It consumed fish eggs suspended in the water column. It consumed newly hatched larvae before they could mature. Each feeding event removed individuals from the next generation, before they had an opportunity to contribute to the future population. This created a subtle but powerful imbalance. Adult fish might still be present, spawning might still occur, yet the youngest stages of life were being intercepted continuously. Every lost egg represented a fish that would never hatch. Every consumed larva represented an adult that would never join the breeding population years later. The effects accumulated gradually, then suddenly became impossible to ignore. Unlike many northern marine species, Periphylla did not confine reproduction to a narrow seasonal window. Throughout the year, new offspring entered the system. While fish populations often depended upon specific breeding periods, the jellyfish maintained a more continuous presence. The pressure never fully disappeared. It persisted through changing seasons, month after month, year after year. Its physical design amplified this advantage. Periphylla possesses some of the largest stinging cells known among jellyfish. Tiny fish larvae, drifting through the water column, encountered a predator capable of capturing them efficiently during the most vulnerable stage of their lives. The impact extended far beyond direct predation on adult fish. It reached into the future of the fish population itself. The consequences eventually surfaced in human communities as well. Fishermen increasingly encountered masses of jellyfish in their nets. Gear that had once targeted commercially valuable species became clogged with gelatinous bodies. Fishing operations grew more difficult and more expensive. At the same time, catches declined. What had begun as an ecological shift became an economic one. Scientific studies examining Norwegian fjords found growing evidence that rising Periphylla abundance contributed directly to declines in cod populations. The relationship was not simple, and no ecosystem changes because of a single factor alone. Yet the influence of the jellyfish became increasingly difficult to dismiss. It occupied a position within the food web that allowed it to affect multiple stages of fish development simultaneously, reducing survival before future generations could establish themselves. Perhaps the most remarkable aspect of the transformation was the absence of resistance. Earlier, the scarcity of predators capable of controlling Periphylla had already become apparent. Within the fjord, that reality carried enormous consequences. Population growth encountered few meaningful biological barriers. The jellyfish expanded into available ecological space, and little existed to reverse the process. The fjord remained beautiful. The mountains still reflected in the water. Currents still moved through the basin as they always had. Yet beneath that familiar surface, the structure of the ecosystem had begun to reorganize itself around a new dominant presence. Periphylla did not conquer through speed or aggression. It succeeded through persistence, abundance, and a life history perfectly suited to exploiting opportunities that the fjord could no longer resist. Not all ecological changes arrive as sudden catastrophes. Some emerge through repetition. A small advantage accumulates, then accumulates again, until an entire system begins to rotate around a new center. What occurred within certain fjords of Norway belongs to this category of transformation. Marine biologists eventually gave the process a name. They called it the jellyfish spiral. The concept was formally described by marine biologist Shinichi Uye in 2008. It refers to a self-reinforcing cycle that can develop when jellyfish populations reach sufficient biomass within a relatively enclosed ecosystem. Once established, the cycle begins feeding upon itself. The conditions that favor jellyfish create more jellyfish, and the increasing abundance of jellyfish strengthens those same conditions in return. At first, the mechanism appears deceptively simple. Jellyfish consume fish larvae and juvenile stages. Fewer young fish survive to adulthood. With fewer adults present, predation on the small organisms that jellyfish feed upon begins to decline. Tiny crustaceans and other planktonic prey become more abundant. The jellyfish now encounter a larger food supply. Better feeding conditions support larger populations. Larger populations consume even more fish larvae. The cycle repeats. Each turn tightens the relationship between cause and effect. Every generation of fish faces increasing pressure during its earliest stages of development. Every generation of jellyfish benefits from a growing abundance of resources and a diminishing number of competitors. What makes the process so powerful is that it attacks recovery itself. Fish populations often possess remarkable resilience. Adult numbers can decline substantially, yet recovery remains possible if enough young survive to replace them. The jellyfish spiral interrupts that replacement process. Larvae disappear before maturity. Juveniles vanish before reproduction. The future population is reduced long before it has an opportunity to become visible. At the same time, the jellyfish population experiences the opposite trajectory. More prey supports greater survival supports greater reproduction produces more jellyfish. The imbalance expands with each passing year. Eventually, the ecosystem crosses a threshold. Ecologists refer to this transformation as a regime shift. The phrase sounds technical, yet the reality is profound. A regime shift occurs when an ecosystem reorganizes around a new dominant structure. The previous balance does not simply weaken, it is replaced. The waters remain the same waters. The mountains still surround the fjord. Seasonal cycles continue. Yet the relationships connecting predator and prey, growth and reproduction, abundance and scarcity have been rearranged into a different configuration. Within a fjord, such changes can be especially persistent because geography limits outside influence. A fjord is not an open ocean current stretching endlessly across the planet. It is a partially enclosed basin shaped by steep walls and restricted water exchange. New populations cannot easily flood in and restore what has been lost. Recovery depends largely upon the organisms already present. When the dominant structure changes, there may be no external force capable of reversing it. This is why the jellyfish spiral has attracted so much scientific attention. Fisheries that have entered such states have often failed to recover even after decades. The conditions sustaining the jellyfish remain intact. The mechanisms that once supported fish populations remain weakened. The system settles into a new equilibrium. For Periphylla, a creature already protected by toxicity, depth, and a scarcity of predators, these conditions can be extraordinarily favorable. The jellyfish does not need to overwhelm the ecosystem through aggression. It only needs to continue doing what it has always done, feeding, reproducing, and surviving. The spiral performs the rest of the work. Over time, the consequences extend beyond biology. Fisheries decline, human communities adapt. Economic traditions built across generations encounter a fundamentally altered environment. Yet beneath these human effects lies a deeper ecological reality. What Periphylla initiates within a fjord is not a temporary disturbance waiting to correct itself. It is a gradual rewriting of the system's operating rules. The flow of energy changes direction. Survival begins favoring different organisms. Relationships that once defined the ecosystem fade, replaced by new ones. And because the process reinforces itself at every stage, the spiral becomes less like an event and more like a destination, a new state toward which the ecosystem steadily settles, turn after turn, year after year. Across much of the ocean, oxygen shapes invisible borders. Animals may never see these boundaries, yet they encounter them constantly. A fish following prey downward eventually reaches water where breathing becomes difficult. A crustacean descending too far enters a layer that can no longer support its metabolism. Entire communities arrange themselves according to the availability of a gas dissolved between molecules of seawater. For countless marine species, oxygen is not merely helpful, it is the foundation upon which every movement depends. Periphylla follows different rules. Among its many unusual adaptations, one of the least visible may also be among the most consequential. Hidden within its tissues are unusually high concentrations of an enzyme known as lactate dehydrogenase. The name rarely appears outside scientific literature, yet its function is profound. The enzyme plays a central role in anaerobic metabolism, a process that allows cells to continue generating energy when oxygen becomes scarce. Most large animals rely heavily upon oxygen to sustain activity. Remove enough of it, and muscles fail, movement slows, and survival becomes impossible. Periphylla possesses a greater capacity to endure conditions that would exclude many competitors and predators. The significance of this ability becomes clearer when considering the geography of the ocean itself. Not all seawater contains equal amounts of dissolved oxygen. In some regions, circulation is limited. In others, biological activity consumes oxygen faster than it can be replenished. The result is the formation of oxygen-depleted layers, often known as dead zones. These waters are not entirely devoid of life, but they impose severe restrictions upon what kinds of organisms can remain there for extended periods. Many fish avoid such regions altogether. Numerous invertebrates do the same. The physiological cost becomes too great. Periphylla can enter them. What makes this remarkable is not merely survival, it is opportunity. Small animals frequently retreat toward oxygen-poor layers because larger predators struggle to follow. Over evolutionary time, these zones became partial refuges, places where prey could reduce the risk of being hunted. The protection was never absolute, yet it was meaningful enough to influence behavior across entire ecosystems. For many species, the edge of a dead zone functioned like a defensive wall. Periphylla crossed it. A jellyfish drifting through oxygen-depleted water encounters prey that may have evolved under the assumption that few predators can reach them there. Copepods, small crustaceans, and other drifting organisms gather within these regions, seeking relative safety. Yet safety depends upon the limitations of the hunter. Periphylla's physiology removes some of those limitations. The consequence is subtle but powerful. Areas once difficult to exploit become available feeding grounds. Ecological space, inaccessible to many animals, remains open to a predator capable of functioning where oxygen levels have fallen beyond the tolerance of others. In recent decades, this adaptation has acquired new significance. As ocean temperatures rise, the amount of oxygen seawater can hold gradually decreases. Warm water retains less dissolved oxygen than cold water. At the same time, changing circulation patterns and increasing stratification can reduce the mixing processes that normally replenish deeper layers. Across parts of the world, oxygen-depleted regions are expanding. The transformation occurs slowly, measured across years and decades rather than days. Yet its effects extend across enormous areas. Water that once supported diverse communities becomes more challenging for fish. Habitats contract. Traditional feeding grounds become less reliable. Boundaries shift. For Periphylla, these changes may create conditions increasingly similar to those it has already mastered. The jellyfish does not require abundant oxygen to the same extent as many of its neighbors. As low-oxygen habitats expand, more of the deep ocean begins to resemble territory where its specialized physiology provides an advantage. The balance tilts, sometimes subtly, sometimes dramatically, toward organisms capable of tolerating conditions that exclude others. There is an irony in this progression. Regions that once offered refuge from predators were shaped by scarcity. Oxygen was limited, and that limitation provided protection. Yet the same adaptation that allows Periphylla to thrive in darkness, scarcity, and isolation also permits it to enter those protected spaces. The boundary remains, but the hunter has learned how to cross it. In parts of the modern ocean, what was once a sanctuary is gradually becoming something else entirely. For the small drifting animals gathered within these depleted waters, the refuge endures only until Periphylla arrives. There is a peculiar danger that follows every successful hunt in the deep ocean. It arrives not during pursuit, nor during capture, but afterward, when the prey has already disappeared into the predator's body. Far below the reach of sunlight, countless animals generate their own illumination. Small crustaceans flash when disturbed. Gelatinous drifters pulse with living color. Tiny organisms suspended in the water carry biochemical lanterns that have evolved over millions of years. In a realm where natural daylight never arrives, bioluminescence has become one of the dominant currencies of survival. Yet light carries a cost. When a predator consumes a glowing animal, the bioluminescence often does not vanish immediately. Chemical reactions continue. Tissues continue to emit light. The meal remains visible long after it has been swallowed. For many hunters, this creates a dangerous problem. A stomach filled with luminous prey becomes a signal radiating through the darkness. Every flash reveals position. Every glow advertises movement. Every pulse announces that something alive has recently fed. In an environment where visibility is otherwise almost non-existent, even a small amount of escaping light can travel astonishing distances. Periphylla encountered this challenge long ago. The solution is woven directly into its body. The same pigment that gives the jellyfish its distinctive deep red coloration is concentrated within the tissues surrounding the digestive cavity. This pigment, protoporphyrin, performs many functions throughout the animal's life, yet one of its most remarkable roles is almost entirely hidden from view. Rather than allowing the light produced by ingested prey to pass through the gelatinous body wall, the pigment absorbs much of that illumination before it can escape. The stomach becomes a chamber lined with darkness. A copepod glowing within the digestive system may continue producing light. A bioluminescent crustacean may continue emitting faint flashes as digestion begins. Yet those signals remain trapped behind a barrier designed not of muscle or bone, but of chemistry. The red coloration visible from the outside is therefore not merely an identifying feature. It functions as concealment. It masks the evidence of recent feeding and prevents the jellyfish from broadcasting its location to anything nearby. This adaptation becomes even more elegant when viewed within the larger context of Periphylla's existence. The pigment already contributes to the animal's appearance. It already plays a role in its unusual relationship with sunlight. It already influences how the jellyfish interacts with the environment around it. Rather than evolving a separate structure dedicated solely to hiding bioluminescent meals, Periphylla uses the same molecular tool for multiple purposes. One solution addresses several problems simultaneously. Such efficiency appears repeatedly throughout life in the abyss. Resources are scarce, energy is precious. Adaptations that serve more than one function often persist because they accomplish more while costing less. Periphylla embodies this principle with remarkable consistency. Its body is filled with examples of structures and chemicals performing overlapping tasks, each contributing to survival in several ways at once. The result is a predator capable of feeding upon luminous organisms without transforming itself into a glowing target. There is another layer to this story, one that creates an unexpected connection between the deep ocean and human biology. Protoporphyrin is not unique to Periphylla. Molecular relatives of the same compound occur within human blood. In our own bodies, related porphyrin molecules form part of hemoglobin, the substance responsible for transporting oxygen through the bloodstream. Every heartbeat sends these compounds coursing through arteries and veins, carrying the oxygen required by living tissues. The relationship is distant, shaped by immense evolutionary time, yet it remains real. A chemical family associated with human respiration also helps conceal prey within a jellyfish drifting through the abyss. The molecule performs different tasks in different creatures, but its presence links lives separated by habitat, anatomy, and hundreds of millions of years of evolutionary history. In the darkness surrounding Periphylla, a swallowed glow disappears behind that crimson shield. The prey continues its final flashes unseen, and the jellyfish moves onward, carrying its hidden meal through waters where visibility can mean vulnerability, and where even the light of a recent feast must be carefully concealed. Winter arrives differently in the far north. It does not descend as a storm or a passing season. It settles over the landscape and remains, stretching day after day until the distinction between morning and evening begins to dissolve. The sun slips below the horizon and stays there. Mountains fade into shadow. Fjords darken beneath a sky that never fully brightens. For months, the cycle that governs so much of life elsewhere simply pauses. In such a place, an animal built around the avoidance of light finds an unusual opportunity. For many years, marine researchers had observed signs that Periphylla was extending its range northward along the coast of Norway. The movement was gradual, almost easy to overlook against the vast scale of the ocean. Yet beneath that slow progression was a larger shift taking place across northern waters, one driven not by the jellyfish itself, but by changing conditions throughout the sea. Then, in January of 2017, something occurred that captured scientific attention. Periphylla was collected inside a high Arctic fjord in the archipelago of Svalbard, a remote region situated between mainland Norway and the North Pole. No confirmed record had documented the species there before. A creature associated with deep, dark waters had appeared in one of the northernmost marine environments on Earth. Its arrival was not the result of a sudden evolutionary breakthrough. Periphylla had not transformed into something new. The animal drifting through the Arctic was fundamentally the same species that had spent ages navigating darkness farther south. The environment had changed instead. One factor was the polar night. During winter, the sun remains below the horizon for extended periods, creating uninterrupted darkness across the region. For an organism whose greatest vulnerability is exposure to light, these conditions remove a barrier that exists almost everywhere else. Waters that would normally become hazardous during daylight remain accessible throughout the day. The fjord begins to resemble the deep ocean. Depth still matters, pressure still matters, temperature still matters. Yet, one of the most important constraints in Periphylla's existence, the constant threat posed by illumination, is dramatically reduced. The animal gains access to portions of the water column that would otherwise become dangerous as soon as daylight returned. A second factor lies within the movement of the sea itself. Warmer Atlantic water has increasingly reached farther north, altering conditions throughout parts of the Arctic. Waters once considered too cold for sustained occupation by Periphylla have become more hospitable. The boundaries that previously limited its distribution have shifted, not abruptly, but steadily. As ocean temperatures rise, habitats are redrawn. Species across the world respond to these changing maps. Some retreat, some decline, some follow the movement of favorable conditions into new regions. Periphylla belongs to the latter group. It does not appear to be forcing its way into unfamiliar territory. Rather, territory that was once unsuitable is gradually becoming compatible with the requirements that have defined the species for millions of years. There is a certain irony in this process. Throughout its existence, Periphylla has remained remarkably conservative in its design. It has persisted through immense spans of geological time with comparatively little change. Instead of constantly adapting itself to new circumstances, it often succeeds because its ancient adaptations continue to work. Now the Arctic is beginning to offer conditions that resemble the world for which those adaptations were originally shaped. During the polar night, entire fjords can exist beneath prolonged darkness. Water masses influenced by warmer currents provide temperatures that fall within the limits the jellyfish can tolerate. The combination creates a setting unusually favorable to an organism whose life revolves around shadow, depth, and endurance. Scientists remain uncertain whether the population observed in Svalbard will become a permanent fixture of the ecosystem. Long-term establishment depends upon many interacting forces, some still poorly understood. Yet the broader pattern remains difficult to ignore. The boundary of Periphylla's world is moving northward, and in some of the coldest waters on Earth, where winter darkness lingers for months without interruption, the ocean is beginning to resemble a habitat this ancient jellyfish has always known. The transformation begins with a raindrop falling far from the sea. It lands on soil, flows through forests and wetlands, gathers traces of organic material, and eventually enters rivers that wind toward the coast. Countless droplets follow the same path. Over years and decades, the process subtly alters the character of the water entering fjords. Nothing dramatic announces the change. No sudden boundary appears. No visible line divides the old world from the new one. Yet the water gradually becomes darker. The effect is deceptively simple. As greater amounts of dissolved organic matter and suspended particles enter coastal systems, incoming light is absorbed more readily. Sunlight that once penetrated deeper into the water column is intercepted closer to the surface. Layers that were previously illuminated become dimmer. Depths that once received scattered traces of daylight receive less. The fjord slowly darkens. For many marine animals, vision is among the most important tools for survival. Fish locate prey through movement and contrast. Predators scan the water ahead, searching for shapes, flashes, and silhouettes. Their success depends upon the ability to see. When light becomes scarce, that advantage begins to weaken. A fish pursuing zooplankton through murky water faces a different challenge than one hunting in clearer conditions. Prey becomes harder to detect. Distances shrink. Encounters become less frequent. Energy must be spent searching for targets that are increasingly difficult to locate. The change may appear modest at first, yet ecosystems are often shaped by small shifts repeated over long periods. A slight reduction in hunting efficiency can ripple outward through entire food webs, influencing growth, reproduction, and survival across many species. Periphylla experiences the same darkening water very differently. Unlike many of the animals with which it competes, it is not primarily a visual hunter. Its world is organized around contact, movement, and disturbance. Minute changes in water flow carry information. Turbulence reveals nearby activity. Chemical traces drift through the surrounding sea. Prey announces its presence through touch, long before it could ever be seen. The jellyfish does not depend upon clear water to function. Its hunting strategy remains effective whether the environment is bright or dim. Darkness does not remove a critical sense because vision was never the foundation of its success in the first place. As conditions shift, the balance between different forms of predation shifts as well. Visual hunters lose some of their advantage. Tactile hunters retain theirs. Over time, the difference can become significant. A habitat that grows increasingly difficult for one group may become increasingly favorable for another. This possibility has emerged as one of the leading explanations for the extraordinary dominance Periphylla achieves in certain fjord systems. The jellyfish did not arrive carrying a revolutionary new adaptation. It did not suddenly become more efficient. Instead, the environment surrounding it may have moved closer to the conditions for which it was already perfectly suited. There is something striking about that pattern. Throughout this story, Periphylla has repeatedly benefited not from rapid change within itself, but from changes occurring around it. Expanding regions of low oxygen favor its unusual physiology. Warmer northern waters open new territory. Extended darkness grants access to environments once beyond reach. Now, darker coastal waters may further tilt ecological competition in its favor. The animal remains fundamentally the same. The world becomes more accommodating. Human activity plays a role in this transformation, even when the connection is difficult to see. Altered land use, changing precipitation patterns, and shifts in watershed dynamics influence what eventually reaches coastal ecosystems. The effects accumulate gradually, often unfolding across timescales longer than a single human lifetime. No fisherman standing on a dock witnesses a fjord darken in a single afternoon. No visitor arrives one morning to discover an entirely different sea. The process advances incrementally, season after season, year after year. Yet some of the most consequential ecological changes occur exactly this way. They arrive without spectacle. They spread without announcement. By the time their influence becomes unmistakable, the underlying transformation has often been underway for decades. And beneath those darkening waters, Periphylla drifts through conditions that increasingly resemble the world it has inhabited for hundreds of millions of years, a world shaped not by sight, but by shadow, touch, and endurance. For much of scientific history, Periphylla existed as a kind of ghost in the records of marine biology. Researchers knew it was there. They knew its shape. They knew fragments of its anatomy. Yet the living animal remained strangely distant, as though every attempt to observe it directly dissolved before reaching the truth. The obstacle was not depth alone. Many deep-sea creatures have been collected, preserved, and studied through traditional methods. Nets descended into darkness, swept through the water, and returned carrying specimens from environments no human could visit. For generations, this approach formed the foundation of deep ocean science. Periphylla presented a different challenge. Its body is composed almost entirely of water. Between 90 and 96% of its mass consists of fluid held within delicate gelatinous structures. The remaining fraction forms tissues, proteins, pigments, and the biological machinery necessary for survival. This architecture functions beautifully in the still pressure of the abyss, yet it proves extraordinarily vulnerable when confronted by mechanical force. A trawl net is not a gentle instrument. As it moves through the water, turbulence forms around every strand and opening. Organisms become compressed, twisted, and pushed against one another. For animals protected by shells, bones, or dense muscle, survival during collection is sometimes possible. For Periphylla, the encounter is often catastrophic. Long before the net reaches the surface, damage has already occurred. Tentacles tear. The bell ruptures. Delicate tissues fragment. By the time researchers examine what has been retrieved, the animal may exist only as pieces suspended in cloudy water. Identification remains possible, but behavior disappears, movement disappears, context disappears. Scientists were left studying remnants rather than lives. As a result, much of what was known about Periphylla for decades came from damaged specimens collected after death or during the final stages of collapse. Measurements could be taken, anatomy could be described, yet the deeper questions remained unanswered. How did it hunt? How did it respond to danger? How did it navigate darkness? How did it interact with others of its kind? The answers arrived not through improved capture, but through a fundamental change in approach. Instead of bringing the jellyfish to the surface, researchers began bringing their observations to the jellyfish. Remotely operated vehicles transformed the study of the deep ocean. Equipped with cameras and precision controls, these machines could descend into environments inaccessible to divers and remain there for extended periods. More importantly, they allowed observation without physical collection. For Periphylla, another detail proved equally important. The vehicles could operate using red illumination. The jellyfish is largely insensitive to red wavelengths of light. To Periphylla, the glow produced by these instruments is effectively absent. Researchers could therefore illuminate the surrounding water without triggering the behavioral responses that brighter, visible light might provoke. For the first time, the animal could be watched living naturally within its own environment. The results transformed scientific understanding. Researchers observed the distinctive movements of the bell as it propelled itself through the water. They watched tentacles fold inward during feeding. They documented the shedding of specialized tissue that continued trapping prey after separation from the body. They witnessed luminous defensive displays and the release of glowing secretions into the surrounding sea. They followed migrations through the water column and recorded patterns impossible to reconstruct from damaged specimens. Even the traveling waves of bioluminescence crossing the surface of the bell became visible in ways no preserved sample could ever reveal. Observation replaced inference. Behavior replaced speculation. The picture that emerged was not merely more detailed, it was fundamentally different. Periphylla ceased to be a collection of anatomical measurements and became an active participant in a living ecosystem, an organism whose survival depended upon strategies far more sophisticated than anyone had previously appreciated. There is a certain elegance in the lesson that followed. For generations, scientists attempted to understand Periphylla by capturing it. The animal's own fragility made that goal nearly impossible. Every effort to possess it physically stripped away part of the information they sought. Only when researchers learned to leave it where it belonged did the deeper story begin to emerge. In the darkness of the deep ocean, drifting through the world that shaped it. Periphylla revealed itself not through capture, but through patience, becoming known at last because science learned the value of simply watching, far from any coastline, beyond shipping lanes, fishing grounds, and the reach of ordinary observation. Vast volumes of ocean water drift through darkness, carrying lives that remain largely uncounted. Among them moves Periphylla, a creature so widespread that it circles much of the planet, yet so elusive that even now its true abundance remains uncertain. Its range stretches across an extraordinary portion of Earth. Periphylla has been recorded in nearly every major ocean basin. It inhabits tropical waters warmed by equatorial currents and survives beneath polar seas where winter darkness can linger for months. It occupies the mesopelagic realm where sunlight begins to fade and extends downward into depths approaching 7,000 meters, a vertical territory larger than many mountain ranges are tall. Most species are constrained by temperature, geography, predators, or the availability of food. Periphylla appears remarkably free of such limits. Wherever darkness persists long enough, wherever suitable water masses drift through the ocean interior, there is a possibility that it is already there. Yet knowing where a creature lives is not the same as knowing how many exist. The challenge has followed Periphylla throughout the history of its study. Traditional collection methods destroy many specimens before they can be examined. Visual surveys reveal only narrow slices of an immense environment. Even remotely operated vehicles, transformative as they have been, observe only tiny windows into an ocean that covers most of the planet. The result is a peculiar scientific situation. Researchers possess strong evidence that Periphylla is widespread, perhaps extraordinarily common, while lacking the tools necessary to measure its global population with confidence. The animal appears repeatedly in surveys from distant regions, emerging again and again from different depths, different climates, and different oceans, as though each expedition is encountering fragments of a much larger story. In certain Norwegian fjords, where conditions favor exceptional success, the scale becomes easier to glimpse. Population densities have been measured at approximately 2.5 individuals within a single cubic meter of water. In practical terms, this means that substantial portions of the fjord can contain jellyfish almost everywhere one looks. The water itself becomes inhabited at a density difficult to imagine from the perspective of the open sea. These concentrations provide scientists with valuable opportunities to study behavior, reproduction, and ecological impact. At the same time, they may represent only one expression of a species whose greatest numbers remain hidden elsewhere. The open ocean offers fewer answers. There, Periphylla occupies a realm so vast that even large scientific surveys cover only minute fractions of the available habitat. Between expedition routes stretch enormous regions that may go years without direct observation. Population estimates, therefore, remain cautious, shaped as much by uncertainty as by evidence. Many researchers suspect that open ocean numbers are substantially larger than fjord populations alone would suggest. The difficulty lies not in proving the animal exists, but in measuring a species dispersed across planetary scales. In the waters surrounding Antarctica, another clue emerges. There, Periphylla reaches some of its greatest known sizes. Surveys of the Southern Ocean have identified it as one of the dominant organisms inhabiting the mesopelagic environment. Beneath drifting sea ice and among cold currents that circle the continent, it occupies a significant ecological presence, woven into food webs that extend across immense distances. This recurring pattern appears wherever scientists look carefully enough. Periphylla is present, sometimes common, occasionally dominant, rarely absent, and yet a strange contradiction remains at the center of its story. Many marine scientists have never observed a living Periphylla with their own eyes. The creature drifts through one of the largest habitats on Earth while remaining unfamiliar even to specialists who devote their careers to understanding the ocean. Its distribution suggests extraordinary success. Its biology explains that success with increasing clarity. Its numbers, however, remain hidden within the darkness it has mastered for millions of years. We know it spans oceans. We know it inhabits depths across the globe. We know it thrives in places where countless other species struggle to endure. What remains unknown is how many millions, or perhaps billions, are moving through those waters at this very moment, suspended beyond sight in a world still far larger than our ability to measure it. A shift measured in fractions of a degree can alter the fate of entire oceans. Not in a single season, nor in a single dramatic event, but gradually, through changes so diffuse they seem almost impossible to notice. A current arrives slightly warmer than before. A layer of water remains separated from the one beneath it, a little longer. Rain falls across a watershed, carrying darker organic material toward the coast. Each change appears modest in isolation. Together, they reshape habitats on a planetary scale, and few creatures appear positioned to benefit from those changes as thoroughly as Periphylla. For most of the species that share its environment, stability is an ally. Fish populations depend on predictable relationships between temperature, oxygen, prey availability, and reproduction. Disturb one element, and consequences ripple outward through the food web. Periphylla has spent millions of years surviving disturbance. Its history is not one of specialization within a narrow set of conditions. Instead, it is a story of persistence across changing seas, fluctuating climates, and shifting ecosystems. Many of the transformations now unfolding in the ocean appear to remove obstacles that once limited its success. Along the Norwegian coast and throughout parts of the Arctic, warmer Atlantic water is extending farther north than it once did. Regions previously constrained by colder conditions are becoming increasingly hospitable. As thermal boundaries shift, the potential habitat available to Periphylla expands with them. The movement requires no new adaptation from the jellyfish itself. The environment changes first. Periphylla simply arrives. At the same time, coastal waters in many regions are becoming darker. Increased runoff from land carries dissolved organic material into fjords and coastal ecosystems, reducing the penetration of sunlight through the water column. What appears to be a subtle alteration in water color can have significant ecological consequences. Many fish rely heavily on vision. Their ability to locate prey depends on available light. As visibility declines, hunting becomes less efficient. Energy expenditure rises while feeding success falls. Periphylla operates according to different rules. It locates prey through contact, turbulence, and chemical cues drifting through the water. Darkness does not diminish these abilities. In many respects, darkness enhances the conditions under which it evolved. As visual hunters lose efficiency, the balance begins to tilt toward predators that do not depend upon sight at all. Another change is unfolding deeper below. As ocean temperatures rise, oxygen concentrations decline in many regions. Warmer water holds less dissolved oxygen, while increasing stratification reduces the mixing processes that replenish deeper layers. The result is the expansion of oxygen, depleted environments, often described as dead zones. For numerous marine organisms, these areas become physiological barriers. Fish retreat. Invertebrates avoid them. Habitats shrink. Periphylla possesses an unusual advantage. Its elevated capacity for anaerobic metabolism allows it to function in environments where oxygen availability would challenge many competitors and predators. Regions that become increasingly difficult for other species may remain accessible to it. In some cases, those regions may even provide opportunities to pursue prey seeking refuge from better oxygenated waters above. These developments intersect with another pattern already observed in several fjord ecosystems. When environmental disruption weakens fish populations, jellyfish can gain an advantage. Reduced predation pressure, altered food webs, and changing habitat conditions can reinforce one another, increasing the likelihood of transitions toward jellyfish-dominated systems. The self-reinforcing processes already documented in certain fjords become easier to imagine across broader regions as climate-driven stress accumulates throughout marine ecosystems. Even direct physiological studies suggest remarkable resilience. Experiments examining the effects of warmer water have shown that an increase of 4 degrees Celsius or 39 degrees Fahrenheit in environmental temperature elevates metabolic demands and activates immune-related responses within Periphylla. The animal experiences measurable stress, yet the warming does not prove fatal. Many species confronted with rapid environmental change face declining survival, shrinking ranges, or reproductive failure. Periphylla responds differently. The pattern emerging from fjords, polar waters, darkening coastlines, and expanding oxygen-depleted zones points toward the same conclusion. Climate change is creating challenges throughout the ocean, but those challenges are not distributed equally. Conditions that disadvantage one organism can benefit another. For Periphylla, each alteration in temperature, light penetration, oxygen availability, and ecological balance represents more than disruption. It represents possibility. The Prince of Darkness was shaped by instability long before humans began altering the climate. In a century increasingly defined by environmental change, that ancient talent for endurance may become one of its greatest advantages. There is a peculiar moment that arrives in the study of any remarkable animal. It comes after years of observation, after thousands of collected samples, after expeditions, surveys, papers, and measurements. The outline of the creature begins to emerge with clarity, yet the closer scientists look, the more empty spaces appear inside that outline. Periphylla has reached that point. Few jellyfish have been examined so extensively in certain regions of the world, and yet the catalog of unanswered questions surrounding it remains astonishingly large. Its movements are known. Its habitat is known. Its feeding strategies, defenses, reproductive patterns, and ecological impacts have gradually come into focus. Yet some of the most basic details of its existence remain hidden. No one knows exactly how long a Periphylla lives in the wild. Growth studies, reproductive data, and population models suggest a lifespan measured not in years, but in decades. The evidence points toward extraordinary longevity for a jellyfish. Individuals continue growing slowly while increasing reproductive output as they age, a pattern consistent with a remarkably extended life history. But no scientist has ever followed a single individual from birth until death. The deep ocean makes such observation nearly impossible. A young jellyfish released into the vast darkness may travel enormous distances through currents, descend beyond observational reach, or disappear into regions that no survey revisits. Lifespan estimates therefore, remain educated calculations rather than direct measurements. The animal has revealed much about how it survives. It has revealed almost nothing about how long that survival ultimately lasts. Its reproduction contains another mystery. Male and female Periphylla appear nearly identical from the outside. There are no obvious visual features that distinguish one sex from the other. Internal examination can reveal the difference, but the mechanism determining whether a developing embryo becomes male or female remains unknown. In many organisms, sex determination follows well-understood genetic pathways. In others, environmental conditions influence development. Periphylla has not yet surrendered that secret. Somewhere within the earliest stages of its life, a decision is made. Science still does not know how. The relationship between Periphylla and light, one of the defining themes of its existence, contains unanswered questions as well. Researchers know that exposure to sufficient ultraviolet radiation triggers devastating physiological damage. They know the reaction involves protoporphyrin and spreads through the animal's nervous system. They know the outcome is fatal. What they do not know with precision is exactly where the boundary lies. How much light is required to initiate irreversible damage remains uncertain. How rapidly that damage progresses under different conditions remains uncertain. The threshold exists, but its exact location has yet to be mapped. Even the flashes of blue-green light that pulse across its body continue to resist full explanation. The possibility that these displays function as communication remains one of the most intriguing hypotheses in Periphylla research. Signals may convey information about location, reproductive readiness, or environmental conditions. They may serve multiple purposes simultaneously, or they may not. The evidence remains incomplete. Observations suggest patterns. Experiments hint at possibilities. Definitive proof remains absent. A creature living in darkness may possess a language of light, yet science has not learned how to interpret it. Another uncertainty extends beyond the animal itself and into the functioning of the ocean. Each night, countless individuals migrate vertically through the water column. They feed at shallower depths and return downward before daylight arrives. Such movements transport organic material through marine ecosystems and may contribute to the redistribution of carbon from upper waters toward the deep sea. Researchers have identified this possibility as an important area of investigation. The extent of Periphylla's contribution remains unknown. Its role in the vast machinery of Earth's carbon cycle may be significant, subtle, or somewhere in between. At present, no one can say with confidence. That may be the most remarkable aspect of all. Humanity has placed instruments on distant worlds. Satellites map planetary surfaces with extraordinary precision. Vast networks of sensors observe weather, climate, and oceans across the globe. Yet within the waters of our own planet drifts one of the most widespread jellyfish on Earth, and some of the most fundamental details of its life remain concealed within the darkness it has inhabited for millions of years. Long before biology became a science, before classifications, diagrams, and carefully drawn evolutionary trees, Periphylla had already settled into its place beneath the ocean. It drifted through ancient seas that no longer exist, persisted through planetary upheavals that erased entire dynasties of life, and carried forward a design that still unsettles many of the assumptions scientists use to understand animals today. The deeper researchers look into its story, the more they encounter a creature that seems to stand slightly apart from the patterns surrounding it. At first glance, it appears simple. It possesses the familiar shape of a jellyfish, a bell suspended in water, trailing structures arranged around a body that seems almost impossibly delicate. Yet beneath that familiar outline lies a collection of contradictions that refuse easy explanation. Most jellyfish follow a life cycle that includes a stationary polyp stage, a period attached to a surface before the free-swimming form emerges. Across the jellyfish lineage, that pattern appears again and again, so consistently that it became one of the defining features of the group itself. Periphylla abandoned it. Its entire life unfolds without passing through the stage that generations of biologists once considered fundamental. The omission is not a minor variation. It is the removal of an entire chapter from the story. The animal develops, grows, reproduces, and spreads across the world's oceans without relying on what appears elsewhere to be an essential biological step. Then there are its eyes. Eyes are usually understood through purpose. They gather information from light. They help an organism navigate, hunt, avoid danger, and interpret its surroundings. Periphylla carries visual organs into an environment where sunlight never reaches and where darkness dominates nearly every hour of existence. The eyes remain. Whether they preserve ancient functions, detect faint bioluminescent signals, or serve purposes not yet fully understood, they endure in a habitat that seems to offer little reason for their presence. Evolution is often described as efficient, yet Periphylla repeatedly presents structures whose complete significance remains uncertain. Its relationship with light deepens the paradox. The animal produces brilliant displays of bioluminescence, sending luminous patterns across its body and releasing glowing material into the surrounding water. Light is woven into its defenses, its behavior, and perhaps even its communication. Yet exposure to sunlight can be fatal. The same creature capable of generating radiance from within spends its life avoiding illumination from above. It creates what it cannot safely endure. Few biological adaptations embody such a striking tension between vulnerability and capability. Its reproductive strategy appears equally contradictory. Across its lifetime, a single individual may release vast numbers of offspring, yet the overwhelming majority perish long before reaching maturity. Entire generations disappear before growing to even 1 centimeter in diameter. By ordinary standards, such losses would seem catastrophic, and still the species thrives. Extreme mortality is balanced by extraordinary persistence. Longevity replaces speed. Endurance replaces efficiency. Success emerges not from protecting every offspring, but from continuing the process across years and decades until survival becomes statistically inevitable. Even its physical construction challenges expectations. Periphylla is composed primarily of water, lacking the armor, skeletons, and muscular power that many animals use to dominate their environments. Its body tears easily. Traditional collection methods often reduce it to fragments. It appears fragile enough to vanish under pressure. Yet this delicate organism has endured through every mass extinction event since its lineage emerged. Continents shifted, climates transformed, oceans reorganized, and countless dominant species disappeared. Periphylla remained. Perhaps that is the most revealing lesson hidden within its story. The principles scientists use to describe biology are built from observation. They emerge from patterns repeated often enough to appear universal. Periphylla serves as a reminder that nature occasionally preserves an older path, one that developed before many modern assumptions existed. It does not seem to violate the rules so much as reveal that the living world has always been broader than the rules themselves, carrying possibilities that have drifted through Earth's oceans for hundreds of millions of years, largely unchanged and still not fully understood. Beyond coastlines, beyond reefs, beyond the narrow band of ocean touched by sunlight, there exists a realm so vast that it reshapes any sense of scale brought from the surface. The deep ocean spreads across most of the planet, occupying more than 65% of Earth's surface and accounting for more than 95% of the living space available to life. Measured by volume rather than area, it is the dominant habitat of our world, a place so immense that even now much of it remains beyond direct observation. Humanity has explored only a small fraction of this domain. Maps of the seafloor continue to expand. New expeditions reveal mountain ranges, trenches, plains, and ecosystems where no human eyes had previously looked. Yet even with satellites, autonomous vehicles, advanced cameras, and decades of oceanographic research, less than 1/5 of the deep ocean has been examined in meaningful detail. Vast regions remain known only through fragments of data and scattered glimpses gathered from instruments, passing briefly through the darkness. Within that immensity lies the mesopelagic zone, the immense band of water stretching from roughly 200 meters to 1,000 meters beneath the surface. This is the region through which Periphylla travels during its daily migrations. It is sometimes called the twilight zone, not because it resembles evening on land, but because traces of light persist there in forms too faint for the world above to imagine. Across the planet, this layer contains an extraordinary concentration of living matter, with estimates suggesting that its total biomass may exceed that of all the world's fisheries combined. Every night, countless organisms rise through these waters. Fish, crustaceans, gelatinous animals, and drifting predators move upward as darkness deepens above them, then descend again when daylight returns. It is one of the largest synchronized movements of life on Earth, unfolding continuously across oceans separated by thousands of kilometers. Periphylla participates in this migration not as an exception but as one member of a vast procession that has repeated itself for millions of years. The scale of what remains unknown within these depths is equally remarkable. Marine scientists suspect that millions of species have yet to be formally described. Some may inhabit remote trenches, others may drift through midwater ecosystems rarely visited by research equipment. Entire branches of biological diversity may still exist beyond the reach of observation, carrying adaptations, behaviors, and evolutionary histories that have never entered scientific literature. Seen within this context, Periphylla changes shape in the imagination. It no longer appears as an isolated curiosity, nor as a singular marvel hidden beneath the waves. Instead, it becomes representative of something larger. Its unusual biology, its ancient lineage, and its mastery of environments hostile to many other animals serve as reminders of how much of Earth's living complexity remains concealed beneath the surface. The deeper scientists investigate the ocean, the more apparent it becomes that familiar coastal waters represent only a thin outer layer of a far greater system. Beneath that layer, ancient rhythms continue uninterrupted. Each evening, Periphylla rises hundreds of meters through the water column. Each morning, it returns to deeper depths. The cycle repeats across ocean basins, through seasons, across generations. It occurred before the first cities appeared. It continued while civilizations rose and vanished. It persisted through centuries when the deep sea was imagined as empty and lifeless. The deep ocean does not depend upon observation to sustain its patterns. Its migrations, food webs, and hidden communities unfold, whether they are documented or not. Long before humans learned to cross oceans, these processes were already underway. Long after individual observers are gone, currents will continue to flow through the abyss, and creatures like Periphylla will continue their journeys through a world beneath the world, vast, enduring, and still only partially known. Far beneath the reach of weather, beneath waves, seasons, coastlines, and continents, a faint pulse travels through the water. It appears for a moment, fades, then returns again. No human witness is required. No audience gathers around it. The signal exists whether it is observed or not. For hundreds of millions of years, long before research vessels crossed oceans or cameras descended into abyssal depths, Periphylla was already producing light in the darkness. That simple fact may be one of the most puzzling details in its entire story. Bioluminescence is often described as a language of the sea. Across the ocean, living light serves recognizable purposes. Predators use it to lure prey. Prey use it to confuse predators. Potential mates identify one another through species-specific flashes and patterns. In many environments, light becomes information, a message transmitted between living organisms sharing the same water. A language, however, assumes listeners. For much of Periphylla's evolutionary history, the deep ocean contained far fewer animals capable of perceiving the kinds of visual signals that dominate modern marine ecosystems. The ancestors of many familiar deep-sea fishes had not yet appeared. Entire groups of visually oriented predators remained far in the future. Yet Periphylla's lineage was already present, carrying within it the machinery required to create luminous displays. The question lingers, like a distant current moving through the darkness. Why produce light in a place where so little could see it? Scientists continue to investigate the functions of Periphylla's bioluminescence, and several explanations remain plausible. Communication between members of the same species remains one possibility. Defensive displays remain another. Signals directed toward potential predators may also play a role in modern ecosystems. Yet, when those explanations are projected backward across immense spans of geological time, the mystery deepens rather than disappears. The waves of blue light that travel across the bell, moving with remarkable coordination, seem almost deliberate in their structure. The glowing particles released into the water during moments of disturbance persist briefly after the animal departs. Elsewhere, subtle pulses move through the margins of the body like information passing from one region to another. These behaviors feel purposeful, yet their original evolutionary meaning remains difficult to reconstruct. Perhaps the answer lies not in communication, but in physiology. Some researchers have suggested that bioluminescence may have originated through internal chemical processes that only later acquired signaling functions. In that view, light production emerged first, and communication followed afterward. What appears today as a message may have begun as something entirely different, a biochemical capability that evolution gradually adapted into a tool. Even so, the image remains striking. For millions upon millions of years, Periphylla drifted through regions of the planet where darkness dominated every direction. Generation followed generation. Ancient oceans opened and closed. Continents separated and collided. Entire ecosystems appeared and vanished. Through all of it, this jellyfish continued producing flashes of blue radiance within an environment that seemed almost indifferent to illumination. There is something profoundly ancient about that persistence. The glow does not depend on recognition. It does not require understanding. It continues regardless of whether another organism responds. In the vastness of the deep ocean, Periphylla releases light into surrounding water, much as it always has, carrying forward a behavior older than many of the animals that now encounter it. Science may eventually uncover the complete explanation. Future discoveries may reveal precise functions, evolutionary pathways, and ecological meanings that transform mystery into understanding. Yet for now, the image remains suspended within the darkness. A pulse of blue light moves across the body of an ancient jellyfish. It fades. Another follows. The signal has been repeated across spans of time, almost beyond comprehension. Through extinctions, climate shifts, and changing oceans, the transmission continues. No answer has yet been fully deciphered. Still, the glow remains. Across spans of time so vast that human history disappears within them, the ocean has repeatedly transformed itself. Coastlines migrated, continents assembled and broke apart. Entire ecosystems emerged, flourished, and vanished. The planet experienced intervals of warmth and ice, abundance and catastrophe, stability and upheaval. Through all of those changes, a lineage of jellyfish persisted in the depths, drifting through ancient seas that existed long before the modern world took shape. The order of jellyfish, known as Coronatae, reaches back at least to the Jurassic period, and jellyfish as a whole possess a history extending more than 500 million years into the past. Their ancestry reaches toward some of the earliest complex animal communities known from the fossil record. Long before forests covered continents, before birds crossed the sky, before flowering plants spread across the land, their soft bodies were already moving through the ocean. Periphylla belongs to that inheritance. Its story is difficult to separate from the immense chronology surrounding it. While countless species appeared only recently in geological terms, Periphylla represents a strategy refined across intervals of time, almost beyond comprehension. It has existed while entire groups of organisms rose from obscurity to dominance and then disappeared again. The fishes evolved around oceans it already inhabited. The great reptiles of the Mesozoic era appeared, diversified, and vanished. The extinction event that ended the age of dinosaurs reshaped life across the globe, yet deep ocean lineages endured through the transition. Mammals expanded into ecological roles left vacant by catastrophe. Oceans changed chemistry. Currents shifted direction. Ice advanced and retreated across continents. Throughout these transformations, Periphylla's ancestors continued drifting through darkness, far below the disturbances, unfolding nearer the surface. Its success did not come from strength. Many celebrated ocean predators achieved dominance through speed, intelligence, size, or aggression. Their stories are dramatic and visible. They pursued prey, defended territories, and occupied commanding positions within food webs. Periphylla followed a different path altogether. It withdrew. Rather than competing for the brightest regions of the ocean, it occupied depths few others could tolerate. Rather than relying upon rapid growth, it embraced longevity. Rather than expending energy continuously, it conserved it. Instead of thriving through abundance, it learned to survive scarcity. Across millions of years, that strategy remained remarkably stable. Go deep enough to avoid many dangers, remain hidden from sunlight, consume opportunities when they appear, reproduce steadily, endure conditions that eliminate more specialized competitors. The pattern is not dramatic, yet over geological time, it has proven extraordinarily effective. There is a lesson hidden within that persistence. Many species become closely tied to particular climates, habitats, or ecological arrangements. When those conditions disappear, the species often disappear as well. Periphylla's way of life depends upon something far older and more stable than surface environments. It depends upon the continued existence of the deep ocean itself. The abyss changes, but it changes slowly. Its darkness remains, its immense pressure remains, its vast distances remain. The fundamental character of that realm has persisted through planetary events that transformed almost everything else. By aligning itself so completely with those enduring conditions, Periphylla attached its fate to one of the most stable environments on Earth. This may explain why it appears less like a temporary resident of the deep ocean and more like an extension of it. Everything that attempted to conquer the abyss eventually encountered limits. Dominant predators vanished. Ancient marine empires disappeared. Entire evolutionary experiments faded into extinction. The deep ocean remained. Periphylla never needed to defeat that environment or rise above it. It never sought mastery over the darkness surrounding it. Instead, generation after generation became more completely integrated into the rhythms of that hidden world. The result is a creature whose history feels inseparable from deep time itself. While other animals seem shaped by particular eras, Periphylla appears shaped by duration. It survives not because it overpowers change, but because it asks so little from the world around it. In the deepest waters of Earth, patience became a biological strategy, and over hundreds of millions of years that patience endured. Long before anyone lowered cameras into the abyss, before research vessels traced lines across remote fjords, before laboratories began untangling the genetics of deep-sea life, Periphylla was already moving through darkness according to a rhythm older than memory. It did not wait for discovery. It did not change because it was observed. Across ages of geological upheaval and biological transformation, it continued the same ancient cycle, ascending through the water column under cover of darkness, feeding where opportunity appeared, then returning to depths where sunlight could not reach. That rhythm continues now. Somewhere beneath the surface, beyond the reach of ordinary sight, individuals drift through waters that have never known a human presence. Their bells pulse, their tentacles spread through the current. Faint waves of bioluminescence ripple across living tissue, unseen by any observer. The animal has no awareness that machines occasionally descend beside it, carrying lenses, sensors, and lights filtered to wavelengths it cannot perceive. It does not recognize the distinction between wilderness and research site. To Periphylla, there is only the environment itself, an immense three-dimensional landscape of darkness, chemistry, pressure, and movement. Yet the indifference of the creature creates a curious contrast with the attention it now receives. Its behavior fills scientific papers. Its migrations are measured. Its expanding populations are tracked across fjords and coastal waters. Fisheries researchers study its influence on fish recruitment. Climate scientists examine how environmental change may favor its spread. Geneticists investigate the unusual biology that has allowed its lineage to endure for so long. Entire teams devote years to understanding an organism that remains completely unaware of their efforts. The relationship moves in only one direction. We study Periphylla. Periphylla does not study us. That imbalance gives the story a significance extending beyond biology alone. The expansion of this jellyfish into new environments is not merely a record of population dynamics or ecological competition. It also reflects a growing realization that many of the systems shaping the planet remain only partially understood. The deeper scientists look into fjords, continental slopes, and mesopelagic waters, the more they encounter processes that have been operating continuously without human notice. The changes observed in places such as Trondheim's fjord emerged from interactions among climate, water chemistry, light availability, oxygen distribution, predator relationships, and countless other variables. No single factor exists in isolation. The appearance of Periphylla in growing numbers was not the beginning of the story. It was one visible consequence of transformations already underway. Seen from that perspective, the jellyfish becomes less a central character and more a messenger. Its movements reveal conditions. Its success reflects environmental shifts. Its expansion traces pathways opened by alterations to ecosystems that people depend upon, yet only partially understand. The animal follows opportunities created by the world around it. It responds to changing circumstances with the same strategies that carried its ancestors through ancient oceans. Nothing in its behavior suggests intention. It does not seek conquest. It does not recognize boundaries. It possesses no awareness of fisheries, economies, or human concerns. When it enters a fjord, it is responding to habitat, food availability, darkness, and survival. The consequences may be profound, but consequence and purpose are not the same thing. This distinction matters. It is tempting to frame ecological change through stories of heroes and villains, winners and losers. Periphylla fits none of those categories. The creature is neither malicious nor benevolent. It is simply successful within conditions that increasingly favor its way of life. In that sense, the Prince of Darkness is not an adversary standing apart from the changes unfolding across the ocean. It is part of those changes, shaped by them and revealing them at the same time. Its presence invites a deeper consideration of the environments humanity influences, the hidden worlds that remain largely unexplored, and the responsibility that accompanies altering systems whose full complexity is still emerging from the darkness. At the mouth of a fjord, the surface can appear unchanged. Water reflects the sky. Tides arrive and depart. Fishing boats follow routes traced across generations. From above, continuity seems effortless. Yet beneath that familiar surface, countless interactions unfold beyond direct observation, shaping ecosystems through processes that are often detected only after their consequences become impossible to ignore. The story of Periphylla leads naturally toward that hidden realm, not because the jellyfish is unique in responding to environmental change, but because it reveals how much of the ocean remains beyond immediate human understanding. Throughout this journey, the animal has appeared again and again at the boundary between what is known and what remains uncertain. Its migrations, its biology, its expansion into new habitats, and its influence on ecosystems all point toward the same realization. The deep ocean is not a distant backdrop to life on Earth. It is an active participant in the planet's functioning, connected to every coastline, every current, and every atmosphere above it. For centuries, human activity has transformed marine environments on scales once thought impossible. Fisheries have harvested immense quantities of biomass. Rivers have carried altered sediments and nutrients toward the coast. Carbon dioxide, released into the atmosphere, has gradually entered seawater. Temperatures have shifted. Oxygen distributions have changed. Layers of the ocean that once seemed permanent have proven more dynamic than expected. Much of this transformation has occurred in places that remain only partially explored. The contrast is striking. Humanity can observe distant planets, model global climate systems, and monitor weather across entire oceans from orbit. Yet vast regions beneath the sea remain largely unvisited. Many deep habitats have never been directly examined. countless organisms continue their lives beyond the reach of regular observation. Even among species that scientists recognize, fundamental details often remain incomplete. Periphylla emerged repeatedly from that uncertainty. Researchers struggled to collect intact specimens. Basic aspects of its lifespan remain unresolved. Important questions about communication, reproduction, and ecological influence continue to be investigated. At the same time, evidence suggests that the environments favoring this ancient jellyfish are becoming more widespread. Darker coastal waters, expanding oxygen-depleted regions, warming northern seas, and altered ecological balances create opportunities that did not previously exist on the same scale. The jellyfish itself is not driving these transformations. It is responding to them. That distinction matters because it shifts attention away from a single species and toward the broader system. When Periphylla appears in growing numbers, it reflects conditions that allow such growth. When it expands into new waters, those waters have already changed in ways that support its presence. The organism becomes a visible expression of deeper environmental processes operating throughout the ocean. Those processes do not remain isolated in darkness. A shift in temperature at the surface influences circulation patterns below. Changes in precipitation affect runoff entering coastal ecosystems. Carbon dioxide absorbed from the atmosphere alters seawater chemistry. The ocean functions as an interconnected whole, carrying the effects of change across depths, regions, and generations. Actions occurring far above the abyss eventually reach places where sunlight never penetrates. In that sense, the deep ocean is not a remote archive preserved from the modern world. It is a living system responding continuously to the conditions surrounding it. Every alteration at the surface sends consequences downward through water, current, chemistry, and time. Some responses emerge quickly, others unfold across decades. And far below, where human presence remains rare and observation remains limited, ancient organisms continue adapting to those changes with the same persistence that has carried them across immense stretches of Earth history. Periphylla drifts through that darkness not as a warning or a symbol, but as a reminder that the edge of human knowledge is still vast, and that beyond it, the ocean continues, shaping its future whether we are watching or not. Far beneath the routes of ships and beneath the reach of storms, there are regions of the planet where day and night have little meaning. The sun rises and sets above them, seasons pass across the surface, civilizations appear and disappear along distant coastlines, yet the waters themselves remain wrapped in conditions that have persisted across immense spans of time. It is within that vast realm that Periphylla spends its entire existence, not visiting it, not retreating there temporarily, but belonging to it completely. For human beings, darkness often feels transitional. It is something crossed, escaped, illuminated, or endured until morning arrives. The deep ocean offers a different perspective. There, darkness is not a temporary condition. It is the environment itself, as fundamental as gravity or water. Life does not merely survive within it. Life is shaped by it, adapted to it, and expressed through it in forms that seem unusual only because human experience is rooted so close to the light. Periphylla stands among those forms. Everything about its existence reflects a long relationship with depths beyond ordinary perception. Its body carries pigments that shield it from dangerous illumination. Its movements follow ancient vertical migrations through layers of water where sunlight fades into obscurity. Its senses rely upon touch, chemistry, and subtle disturbances moving through the surrounding sea. Even its flashes of bioluminescence emerge from a world where vision operates according to different rules than those familiar at the surface. Yet, despite the unfamiliarity, there is a remarkable continuity to its life. It feeds, it grows, it reproduces, it navigates its environment. It encounters competitors, prey, and occasional predators. Generations follow one another through centuries, then millennia, then spans of time so large they challenge ordinary imagination. Long before human languages existed, Periphylla and its ancestors were already participating in these rhythms. Long before maps, nations, cities, or written history, the same migrations continued through deep water. The persistence of that existence reveals something important about the ocean itself. From the surface, the abyss can appear empty simply because it conceals what it contains. Human perception often interprets absence of visibility as absence of activity. The deep sea demonstrates the opposite. Beneath the illuminated layer of the world lies an immense living system filled with interactions, movements, adaptations, and relationships unfolding continuously beyond direct observation. Periphylla serves as a reminder of that hidden abundance. The jellyfish is not surviving in spite of the darkness. It is thriving within the conditions that darkness provides. The cold temperatures, immense pressures, and vast distances separating individuals from one another are not obstacles imposed upon the species. They are components of the environment that shaped it across evolutionary time. The ocean created the circumstances. The animal emerged from them. When people encounter Periphylla through images captured by deep-sea cameras, the reaction often stems from its apparent otherness. Its glowing body, crimson pigmentation, unusual biology, and ancient lineage seem distant from familiar forms of life. Yet that sense of distance may reveal more about human perspective than about the jellyfish itself. Most human experience unfolds within a remarkably thin layer of the planet. We inhabit coastlines, valleys, plains, and mountains exposed to air and sunlight. The environments most familiar to us represent only a fraction of Earth's living space. Beyond that narrow zone lies a world of extraordinary scale, much of it cold, much of it dark, much of it still only partially explored. From that broader perspective, Periphylla appears less like an exception and more like a participant in the dominant conditions of the planet. Vast regions of Earth exist beyond sunlight. Vast regions remain untouched by direct human presence. Vast regions continue their biological processes regardless of observation. The jellyfish belongs naturally to that reality. Its existence is neither mysterious nor misplaced within the ocean that produced it. If there is strangeness here, it may lie in the realization that the familiar human world occupies only a small corner of a far larger living planet, while creatures such as Periphylla have spent hundreds of millions of years at home in the darkness that surrounds it. At this moment, far below the routes of ships and beyond the reach of weather, a single Periphylla is moving upward through the water. No witness accompanies it. No sound marks its passage. The journey unfolds according to instructions written into its biology across spans of time so vast that human history occupies only the thinnest fraction of them. Hours earlier, it rested in deeper water, surrounded by conditions that have shaped its lineage for ages beyond counting. Now it ascends through the darkness once again, crossing layer after layer of ocean in pursuit of prey. The movement is neither decision nor ambition. It is a rhythm, ancient and enduring, repeated by countless generations before it, and repeated tonight by countless others scattered across distant oceans. Soon it will encounter drifting life suspended in the water column. Tentacles will spread, contact will be made, feeding will begin. If threatened, the jellyfish may release its luminous defense, sending blue radiance into the surrounding darkness. If left undisturbed, it will continue its journey until the cycle turns once more and deeper water calls it home. Nothing about this process is new. The ancestors of Periphylla performed similar migrations long before forests covered the continents in their modern forms. They drifted through ancient seas while mountains rose and eroded, while oceans opened and closed, while entire groups of animals emerged, flourished, and disappeared. Through every transformation, the pattern endured. Civilizations appeared above them. Empires expanded and vanished. Languages formed, changed, and were forgotten. Yet the migrations continued. The jellyfish possesses no awareness of these events. It does not know that cameras now follow members of its species into places that once seemed unreachable. It does not know that scientists analyze its genetics, map its distribution, or debate its ecological influence. It has no understanding of warming oceans, altered coastlines, expanding dead zones, or darkening fjords. And yet, those changes matter. Across parts of the modern ocean, conditions increasingly resemble environments in which Periphylla thrives. Waters once less suitable become more accommodating, boundaries shift, habitats expand, opportunities emerge. The jellyfish responds exactly as it always has, not because it understands change, but because adaptation was woven into its history long ago. There is something remarkable in that simplicity. Human beings often imagine survival as a struggle, requiring constant innovation and reinvention. Periphylla offers another perspective. Across immense stretches of deep time, its success has come from persistence. It found a way of living compatible with one of the largest habitats on Earth and remained faithful to it. The darkness provided shelter. The depths provided stability. Patience proved more durable than speed, strength, or dominance. Above, the human world continues its restless motion. New technologies appear. New questions emerge. New attempts are made to understand regions that remain largely unexplored. Each generation pushes observation a little farther into the abyss, illuminating another fragment of the hidden ocean. Yet even now, much remains beyond direct knowledge. Vast expanses continue their existence without witness, carrying on according to processes established long before humanity arrived. Periphylla belongs to that continuity. The deep ocean existed beneath every civilization that ever gazed across the sea. It lay beneath moments of discovery and moments of loss, beneath migrations, conflicts, celebrations, and dreams. Throughout it all, ancient organisms continued their lives in darkness, participating in cycles older than memory. The jellyfish remains one of them. When this night passes and another begins, migrations will continue. Blue flashes will appear and vanish in unseen water. Countless individuals will rise and descend through the depths according to the same enduring rhythm. The story does not conclude because a camera records it or because a scientist describes it. The ocean continues beyond observation, and somewhere below, beyond the reach of sunlight, Periphylla will keep doing what it has always done, glowing briefly against the darkness, feeding, descending once more into the abyss, and carrying its ancient rhythm forward into a future it will never know, but one it has already been crossing for hundreds of millions of years.